Which of the following would you expect to give the largest yield of a para-substituted product if used as a substrate for an electrophilic aromatic substitution reaction? So the first thing we're going to want to do in approaching this problem is to identify any of these groups that might be ortho-para directors. So your ortho-para directors are your electron donating groups. Or mostly your electron donating groups. There are the halogens, which are an exception. So your electron donating groups, you're going to recognize these as groups that can donate electrons via resonance. So they would have a lone pair of electrons on an oxygen or a nitrogen that can donate into the ring. So on oxygen or nitrogen is where you're going to have the most efficient electron donation. So if we look at a group like we have here for C, we've got these lone electrons in the oxygen that we can push into the ring. And so this is making the ring more activated. It's putting a negative charge onto this ring, and specifically, it's dispersing this negative charge on the ortho and para positions, which is what makes those positions more nucleophilic. So we can see the resonance there with the lone pair of electrons on that ortho position. And we can push it around the ring to see that we can donate these electrons also to the para position. And we can draw one more resonance structure that shows us that we can also push them onto the other ortho position. So what we're doing by putting the negative charge on these positions is we are making these positions more nucleophilic. And it is the ring itself that is the nucleophile in an EAS substitution reaction. So we can see that we have the greatest electron density on those ortho and para positions. Okay, so that explains why this is an ortho-para director. We haven't quite answered the question of the largest yield of a para-substituted product because we have other groups here that are also electron donating and ortho-para directors. So this is one pattern. These will make for your more strongly activated ring systems when you have a lone pair of electrons on oxygen or nitrogen that can donate. You could also have an alkyl group. So a carbon-based group, and we've seen how carbon groups stabilize things like positive charges back when we looked at carbocations. So that means we've got an alkyl group here on A, that's also an ortho-para director, and then we've got the tert-butyl group here on D, which is an ortho-para director as well. And so being this large group, this is actually going to physically block those ortho positions. So if you have a highly branched alkyl group like this tert-butyl group, you're going to get most of your electrophile adding to the para position. So this is the answer to our question, what would give us the largest yield of the para substituted product. And of course, B is an electron withdrawing group. So this is the exact opposite effect of what we saw in the resonance here. So this is a meta director. So we drew some resonance to explain why something with a lone pair of electrons on oxygen or nitrogen could donate in and be an electron, to be an electron donating group and ortho-para director. To explain why alkyl groups are ortho-para directors and electron donating, we need to look at the carbocation intermediate of the EAS reaction. So I'm going to draw something with an alkyl group. We'll just use a general R for our alkyl group. Okay. And if we substitute with an electrophile, so the benzene ring itself is what's going to be the nucleophile. And so I'm going to do the attack from the ortho position for this example. So we're going to add that electrophile to the, to the para position. We could have also shown it with the ortho positions and we'd end up with the same sort of scenario. So here we have a positive charge and we have our new electrophile that we've added. And so what we want to see is how does this R group help to stabilize the positive charge? And so we know that more substituted carbocations are more stabilized. And so what we see here with the resonance is when we've added the electrophile to this para position or to the ortho positions, that we're able to have a resonance structure that puts this cation right here where it can be stabilized by that R group. So let's take a look at that resonance structure that explains this. Okay, so we've moved this pi bond over. We still have the pi bond here. And in this way, we're able to put the positive charge where it can be stabilized by that R group. And so that's a carbocation essentially, right? So this is just hypoconjugation from that R group is helping to stabilize that positive charge.